Hi, everyone. This is Professor Monty. I just wanted to welcome you back to our lesson. Today, we're doing sections 9.4 and 9.5. So we're actually physically jumping into the hypothesis testing. So let me just do a couple quick reviews to get us started. Recall for a hypothesis test. Let's list the steps down. Hypothesis test steps. Now notice the title of this. We're doing hypothesis tests for one population mean when sigma is known. Remember, sigma is the population standard deviation. In this section, we're going to have the population deviation. In the next section, we will not have the population standard deviation. So in other words, if we have the population standard deviation, we're going to do a z-test. If we don't, and we'll see that in the next section, we'll do a t-test. But we'll get there shortly. But let's talk about the steps of the hypothesis. First step, you always have to state your null hypothesis H sub 0 and your alternative hypothesis H sub A. All right, that's the first step. Always have to do it. 2, determine significance level alpha. Now, I talked about this in the last lecture. The significance level alpha, that's our probability of making a type 1 error. In other words, rejecting the null hypothesis when it was really true, and we shouldn't have rejected it. This is always going to be given to us. If it's not given, we're going to use 5%. All right. Third step, we're run our test on the calculator to find z. Oops, to find p-value. Now in this section, we will find z as well. We're just not actually going to physically use z. They will ask for z on your homework, so I'll point that out when we get there. All right, the fourth step is we're going to come to what we call our decision. And our decision is either to reject the null hypothesis or do not reject the null hypothesis. I don't know where that all went. Or do not reject the null hypothesis. And remember, that's based on the p-value. If the p-value less than or equal to alpha, we reject the null hypothesis. If it's not less, we don't reject the null hypothesis. Okay, and then our fifth step, we answer the question that was asked. Answer question with yes or no. And state conclusion. All right, and we'll go through all these steps. And I've listed these steps in the previous lecture, so you've probably seen these. I expanded a little bit on some of them. But that's the basic idea. And from here, that's all the information we need to know. I will show you how to find the p-value on the calculator. So we'll do that. If you read through the book or if you go to a tutor, they may try to teach you a completely different way. Even if you're online doing the homework and you click on help me solve this, if it starts to take you to a table or if it's showing you formulas, that's not the way we're learning how to do it in this class. We're letting the calculator do the computations. We're just doing the interpretations. So what we do in statistics is we have to decide what test to run. We run the test, we come to our conclusion. We state the results. This class is not set up to be a computation class, which many statistics classes are. I want you to understand statistics so you can actually use it. Okay, so let's jump into a problem. I will refer to the problem. And the first problem we're going to do is, and let me make sure that I get these in an order I'd like to get them. It's problem 988. So let's get this out of the way. So we're doing problem 988, and it's on page 398. All right, let me read it. It says worker fatigue. A study by M. Chen et al. Titled Heat Stress Evaluation and Worker Fatigue in a Steel Plant assessed fatigue in steel plant workers due to heat stress. A random sample of 29 casting workers had a mean post-work heart rate of 78.3 beats per minute. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean post-work heart rate for casting workers exceeds the normal resting heart rate of 72 beats per minute? Assume the population standard deviation of post-heart work rates for casting workers is 11.2 beats per minute. So let me write down some of the vitals here. It says a random sample of 29 casting workers. So first of all, we know N is 29. That's my sample size. They had a mean heart rate. Now it's those 29. So the mean heart rate is X bar, the sample mean, of 78.3 beats per minute, BPM. At the 5% significance level, so 5% significance level, that's alpha. Okay, alpha, and 5% we'll just write as 0.05. Do the data provide sufficient evidence to conclude that the mean post-work heart rate for casting workers exceeds the normal resting rate of 72 beats per minute? We'll just simplify it and we'll say, does heart rate exceed normal level of 72 beats per minute? That's the question. That's the question we want to answer. Now notice 72 beats per minute is the average. They had 78.3. Clearly the sample average is bigger than what this population average is. The question is that just due to sampling error, or is it because of the heat that they're exposed to? So we don't know just looking at the numbers. We expect a sample mean to be different than a population mean. But is that too different to say it couldn't just be sampling error? Remember, sampling error is just the difference between a population number and a sample number just due to random selection of our sample. Okay, so that's what we're going to test. Realize when you look at data in the media, a lot of times they'll just give you that sample number and they'll say, oh, look, clearly it's higher. Their rate of our sample was 78.3, but we have to be an intelligent consumer and say, well, statistically, how likely is that to occur? Is that due to chance, or is it clearly because they're working in this heat stress environment? Okay, so we're going to do that. Here's the basic idea that this 5% significance level, what that is saying is that if the odds or if the percent chance, the probability that our sample mean would be so far above our population mean, if that probability is less than 5%, assuming that 72 was what we expected the population rate to be, if that population gives me a percentage or a proportion, if that probability is less than 5%, we're going to say it's too unlikely to happen by chance. It must be due to other reasons. Those other reasons being that heat environment. Okay, so let's go. So there's my question. We're ready for the hypothesis test, although they did tell us one other thing. They said this population standard deviation. Now this is important. It's the population standard deviation. They actually said population. The reason I'm pointing that out is because that's sigma. They told me sigma was equal to 11.2 beats per minute. Let's see, beats per minute. Now that's important because if that's the sample standard deviation, we don't do a z-test, we do a t-test. So you do have to make sure you understand which standard deviation they're talking about. Okay, we're ready for the test. All right, so there's everything they told me. There was one other thing they told me before the reading of this section, because notice I didn't say anything about this being normally distributed, and my sample size is below 30. So we know that if the sample size is 30 or larger, we can assume that the sampling distribution of all means of size 30 or bigger are normally distributed, but they didn't say that. But before all this reading, it says, before problem 983, it says preliminary data analyses indicate that applying the z-test is reasonable. So that's for problems 983 through 988. Okay, so they're telling us we can use z. One of those assumptions that has to be true is that it's normally distributed. Okay, so there's the setup. A lot of talking, but we haven't done a hypothesis test before. Here's where the hypothesis test starts. Step one, list our hypotheses. The null hypothesis, we always assume that what it was is what it is. They said the mean heart rate of the population was 72. We're going to assume that this population mean is 72 beats per minute. The null hypothesis will always include an equal. The alternative hypothesis, population mean, is the answer to the question. Does the heart rate exceed? Well, that means is the mean greater than 72 beats per minute? I am having a little bit of problem doing my beats per minute. Let's see. Beats per minute, okay. So there's my first step. I listed, stated the hypotheses. Second step, we need to know the significance level. Well, we already said alpha 0.05. Again, that'll be given to us. Third step, now we have to run our test. The test we're going to do is a z-test. From the z-test, a couple things we're going to get at. One, we're going to get the z-value, which we don't use, but it's the z-value that they calculate the p-value from. So they'll ask you on the home, what's the z-value? So we'll state that off to the side, but what I care about is the p-value. All right, so what we need to run to the calculator to do all these calculations. So let me pull that up for you real quickly. All right, here's our calculator. So we're gonna base things on this. So here's how we run that test. Let me have to look back in the book at the values again. So we're gonna go stat, tests, just like we did for t intervals and z intervals, except 1 and 2 are the z-test and the t-test. This one's a z-test, so I'm gonna press 1, and notice right at the top it says z-test. That's what I want. It's flashing stats because for the input, I either have to tell them I have the statistics, which I have, or if I have the raw data, then I would put that in. I'd have to have my data in list 1 or list 2, wherever I put my data. So I'm in the right spot right now. I'm in stats, so I'm just gonna arrow down. I'm gonna answer these questions. The first thing says, well, what's the mean? Notice that's the population mean mu, but it's got that sub-zero meaning from the null hypothesis. What are we assuming the mean to be? And we're assuming the mean to be that 72. So I'll hit enter. It'll take me down to sigma. Notice it says sigma because we have to have the population standard deviation to do a z-test. They said that was 11.2 beats per minute. That's one too many twos. Let's see, we'll delete that one. So 11.2 beats per minute. What was X bar? Oh, the sample mean was 78.3. What was our sample size? Oh, we had 29. And then this mu down here is what our alternative hypothesis was. Remember, we said we thought mu was greater than the original mu sub 0 from the null hypothesis. So we pick the one that says greater than, just like we wrote on our alternative hypothesis. And then we just come down here and calculate. That p-value it gives us is what we want. So it's going to give us two things. And I'm just going to jot these down on a piece of paper so that I have them with me so I don't have to flip back. But the z-value, 3.03, if we round it to 2 decimal places, the p-value a lot of times will go to 4 decimal places, so I'll go 0.012. All right, so let's flip back over, but that's as hard as the calculation is. The calculator does the calculation for you. You just need to know all the steps. All right, so the z-value it gave me, 3.03. The p-value, 0.0012. Now think about that. As a percent, we move the decimal twice. It's 0.12%. So there's almost no chance that we would get these results if the null hypothesis were true. So we compare the p-value, we compare that to 0.05, which was my alpha. And remember, the rule is if the p-value is less than alpha, we reject the null hypothesis. So that's my fourth step, is to say, for reject the null hypothesis. I don't know where that E came from. So we reject the null hypothesis. I apologize for that E. I don't think I know how to get rid of it. Or what if I do this? And I wonder if I can clear it. Delete. All right. So that's gone. Okay. Oh, I don't want that up. Okay. So I rejected my null hypothesis because it was less than the 5% that I had for alpha. Remember what that 5% says. I'm assuming the null hypothesis is true, that mu is equal to 72 beats per minute. And unless the p-value I get, which think about it as the probability that the null hypothesis is true. We're saying, oh, the probability the null hypothesis is true is less than 1%. That's well below the 5% cutoff I stated. So I'm going to reject the null hypothesis and say, hey, I don't think it's true. And if it's not true, I go with the alternative hypothesis. So I don't think mu is equal to 72. I go with the alternative. I think mu is greater than 72. And so my conclusion is, to answer the question that says, does heart rate exceed normal level of 72 beats per minute? I'm going to say yes. And then state the conclusion. It appears the average heart rate exceeds 72 beats per minute. And so that's my conclusion. I've shown statistically that yes, that's probably the case. Now, that's the end of the hypothesis test. For those of you that are curious about how the z-value and the p-value are related, here's the idea. Remember, we assume it's normally distributed population. I'm going to start off with my mean that I assume to be 72. I got my X bar value of 78.3, so it was over here someplace. I found out that that 73.2 gave me a Z value of 3.03. That's the Z value I found. In other words, 78.3 is 3.03 standard deviations above the mean of 72. If I start at that value and look at that value plus anything more extreme, and I find this area, that area, remember, is equal to the probability, that's what we call the p-value. So the p-value is actually that area. So technically for the p-value, it's the probability I would get a value that far from the mean or further from the mean if the null hypothesis were true. So if mean really was 72, what's the probability I would get 78.3 or something further? Well, it was only 0.12% or a probability of 0.0012. So that's why I rejected and said, I don't think it's true. All right, so that's the hypothesis. We're gonna do some more of these, but I'm gonna go a little bit quicker since we've seen one. All right, now this next one we're gonna do, it's also in 9.4. There's gonna be a little bit more to it because they give us the data this time. So I want you to make sure that we know how to do the one with the data. So this is problem 986. I'm not gonna write down the data, but I'll show you entered into my calculator. So if you wanna follow along and enter the same numbers, you can. This is on page 397. All right, let me read it to you first of all. It says early onset dementia. Dementia is the loss of the intellectual and social severe enough to interfere with judgment, behavior, and daily functioning. Alzheimer's disease is the most common type of dementia. In the article, Living with Early Onset Dementia, Exploring the Experience and Developing Evidence-Based Guidelines for Practice, P. Harris and J. Keaty explored the experience and struggles of people diagnosed with dementia and their families. A simple random of 21 people with early onset dementia gave the following data on age at diagnosis in years. Okay, so they're going to give me the data. I'm not going to write it down again. I'll just enter it into my calculator. And it says, the question says, at 1% significance level, so that's alpha, so alpha equals 0.01. Do the data provide sufficient evidence to conclude that the mean age at diagnosis of all people with early onset dementia is less than 55 years old? So at 1% significance level, does data provide sufficient evidence that mean age at diagnosis of dementia is less than 55 years old? All right, so there's my question. They give us the data. They do say, they give us a note on this in the book. They tell us what X bar is, but we're not going to use it because we're going to enter the data this time. They do say, though, assume the population standard deviation. Assume population standard deviation. Again, that sigma is equal to 6.8 years. All right, so that's all I'm going to need. But I'm going to enter the data into list one. All right, so let me go ahead and do that. I'm going to flip over real quick. All right, so let's go in here. Let's go into the calculator. Let me clear what we have in there. So I need to enter everything in list one. So I'm going to go stat, edit, and then list one has stuff in there. Let's arrow up to where it says L1, and I'm going to clear that. Remember, don't hit delete. You'll get rid of the whole list. I'm going to hit clear, and then when I arrow down, I can put that in. Okay, here's my data that I'm putting in. I'll read it out as I do it in case you want to just follow along. 60, 58, 52, 58, 59, 58, 61, 61, 54, 59, 55, 53, 44, 46, 47, 42, 56, 57, 49, 41, and 43. All right, let's see, 1, 2, 3, 4, 5, 6, 7 by 3, 21. So we've got 21 data points in there, so we look good. I'm just gonna scroll up real quick, make sure everything's a 2-digit number, or I'll just scroll from the bottom. That'll flip me back over. Yeah, everything's 2-digit number. It looks like I put it in well. So anyway, hopefully you got all those numbers in there. Let me just, so there's the top, if you want to take a picture of that to make sure you have all the numbers, and then I'll flip, there's the bottom. I guess there's the bottom if I go one more. So there's 21 ages in there. Okay, so now I go back to what I did before. I go stat, test. All right, now before we do the test, I'm gonna flip back over. We're gonna start our hypothesis test. We're already here. Let's not do that. Let's go ahead and run the test. All right, so the test I'm gonna do, it's still a z-test, so you can hit either 1 or hit enter, but it says z-test. But this time, notice we have the data. So go to where it says data is flashing and hit enter. Now it changes it because it gives us this list 1 over here to put the data into. So anyway, we go down. It says mu sub 0. That's from our null hypothesis. And I didn't write those down. Maybe I should have, but we'll go write that all down together. The question says at the 1% significance level, do the data provide sufficient evidence that the age is less than 55 years old? So we're going to assume that it's equal to 55 years old. The standard deviation they gave me was 6.8 years. Our data is in list 1, so we're okay. Leave frequency at 1. Come down here, they said, is the age less than, so we have to go to where it says less than. Hit enter to select that. We want to see if the age is less than 55 years old. So now we go down to calculate, hit enter. Again, there's our Z. If you want the Z value, go ahead and jot that down. I will jot that down because they will ask us that. So let's see. Z equals negative 1.35 because we have to round up. The p-value this time, 0.0889. Again, we have to round up. Now, notice one thing they did. They calculated X bar for us. And notice X bar is 53. So the sample means 53, which was less than 55, but is that less than by enough? We don't know. That's why we check the p-value to see what's the probability that we would get 53 if the population mean really was 55. Okay, so they calculated the sample standard deviation, irrelevant because we already had the population standard deviation, but since we had the data, they just calculated that for us. Okay, so now let's go back and do our test. So we've entered our data. So our hypothesis test, we still have to go through the steps. So step 1, the null hypothesis, we're assuming the mean is 55. The alternative is what the question asked. They think it might be less than 55 years. Okay, significance level again, if you want to write that, we had 0.01. But then we did the hypothesis test. We did a z-test. Oops, that's not very good. Let's erase that. Looking for my eraser. There it is. We did a z-test. And we actually got a z value, which I'll write down since I jotted it down, negative 1.35. But it's the p-value that we're going to use. Our p-value was equal to 0.0889. Again, if you think about that as a percentage, it's 8.89%. We check to see if that's less than or equal to 0.01, which was my alpha, which is a 1%. Notice this is not less than alpha. So I'm going to cross that out. I'm going to say, no, it is not less than or equal to. I did not that. It's not less than or equal to, so we don't reject the null hypothesis. So step 4, we're going to say, do not reject the null hypothesis. All right, again, let's think about what just happened. We said I've got a cutoff of 1%, that's alpha. If my p-value is less than 1%, if the value I get from my sample mean would happen less than 1% of the time, I'm going to reject the null hypothesis that mu really is equal to 55. And I'm going to go with that, whatever I said the alternative was. Okay, again, another way of looking at that is we have our level at 1%. Anything less than 1% chance of the null hypothesis being true, we're going to throw away. Well, we found out the chance of the null hypothesis being true is actually 8.89%. So we say, oh, that's not less than 1%. It's not rare enough. It may have happened just due to sampling error. We don't have strong enough evidence to say that mu actually is less than, it might just be sampling error. So since we didn't reject the null hypothesis, we have to say no, the data is not sufficient to show, and I'm not going to word the whole thing, to show the average age. I think they said the mean age is less than 55. Do we think maybe the average age is less than 55? Yeah, maybe our sample mean was 53. But that wasn't far enough to prove at the 1% significance level that the mean actually was less than 55. Notice, had alpha been a 10% significance level, we would have rejected the null hypothesis because it was less than 10%. So that one's kind of right in that gray area. Oftentimes what they'll do in research is they won't state the conclusion for you. They will tell you the p-value and let you come to your own conclusion as to whether you feel that's significant enough. So since they had stated alpha was 1% in this case, we do not reject. No, the data is not sufficient to show the average age is less than 55 years. Okay, so that's the end of 9.4. We did a couple examples in there. I'm going to go into 9.5. There's just one change in 9.5. We'll do an example or two in there so we get an idea what's going on. So let me kind of back out of this. I'm going to go to 9.5. We'll start on a nice clean sheet. So this time we're doing a hypothesis test for one population mean, but this time sigma is unknown. So let's state it this way. If the population standard deviation sigma is unknown, we use the sample standard deviation S and a t-test. We don't use a z-test. We only use a z-test if we know sigma. So let me put a note right here. Note. I keep hitting the erase button. If we know sigma, use z-test. If we don't know sigma, use a t-test. Now notice we're saying we don't know sigma, but we do know the sample standard deviation S. So don't think just because they tell us a standard deviation that it's a z-test. If they're telling us the sample standard deviation, it's a t-test. All right, that's the only difference between last section and this section. Now, I say the only difference. There's one thing they're going to ask you on some of the homework. They're going to ask for what they call let's put this over here. They're going to ask for what they call the degrees of freedom. And all you need to remember, they denote it DF. Here, I'll put DF here so we know that that's still degrees of freedom. The formula for that is just n minus 1. That's something they use to calculate the value of t so they can figure out what the p-value is. But for our purposes, we just have to know degrees of freedom is n minus 1. The idea is, say I have a sample size of 3. I get to pick any of those 3 as my first member of the sample. And then I get to pick another one in the sample. Then I only have 1 left. I don't have any freedom to pick anymore because there's only 1 left. There's no choice. So if I had 3 to pick from originally, I only get to pick the first 2. The third one is determined for me. So the degrees of freedom there would be 3 minus 1 is 2. And so that works for any sample size. That's what that represents. I just want you to be able to do it when they ask you the question on the homework. So other than that, I won't refer to degrees of freedom at all when I do these problems. All right, so let's jump into a problem. Let's see. So I'm flipping through. All right. So let's start with this one. This is problem 9-114. It's on page 406. All right. And it says this: golf robots. Serious golfers and golf equipment companies sometimes use equipment testing labs to obtain precise information about particular club heads, club shafts, and golf clubs. Ooh, golf balls, excuse me. One golfer requested information about the Jazz Fat Cat 5-iron from Golf Laboratories Incorporated. The company tested the club by using a robot to hit a Titleist NXT Tour ball 6 times with a head velocity of 85 miles per hour. The golfer wanted a club that on average would hit the ball more than 180 yards at that club speed. The total yards each ball traveled was as follows. So they give us the data here. I will give you the data myself because it's a nice small set and it's good to be able to refer back to the data. So 180 yards, this is how far the ball went. 187 yards, 181 yards, 182 yards, 185 yards, and 181 yards. That's all the data they had. Now, the nice thing about having a robot, it's very consistent. You can see the consistency here with how far the ball traveled. All right, so that's our data. They do tell us, well, here's part A. Let's read the question. At the 5% significance level, at 5% significance level, do the data provide sufficient evidence to conclude that the ball does what the golfer wants? Does ball, now let's interpret that, because the golfer wanted the ball to go, let me read it again, that would go more than 180 yards. Does ball average more than 180 yards? That's the question that we're going to ask. Now they tell us, it says, note, the sample mean and sample standard deviation of the data are. Now they give us those. We don't need that because we have the data. So the calculator will calculate the mean of the sample and the standard deviation of the sample because we have the data. So we don't even need any of that information. They give that to people that don't have technology to use to make it a little bit easier to do all their calculations by hand. All right, so we don't need that. So we're just going to go ahead and do the problem. So again, what's the first thing we do? We state the null hypothesis. The null hypothesis was that the population average was equal to 180. Remember, we always have an equal for the null hypothesis. We're going to assume things are as they stated. The alternative is what we're trying to show, that the mu is actually greater than 180 yards. All right, so that's where we're starting. I've got that data. Oh, I don't have to take a picture of it because I still got it in my book. I can just write it down. So there's my null and alternative hypothesis. I'm not going to number these anymore. You can number them if you want to. We do know that alpha was stated at 0.05. Remember, that was the significance level up here. I'll put these numbers here real quick for us. 3, this time we do a t-test. And we do a t-test because we don't know the population standard deviation sigma. We're going to calculate the sample standard deviation based on the data. So we're doing a t-test, and I'll even put over here t equals. So we're going to see that when we do the test, but let's go ahead and do the test. All right, so we're going to flip this over, go back to the calculator, go back to the calculator. Let me clear that. Now this time I'm going to go stat test, but it's the second one down, t-test. So I'll select that. Notice on the top it says t-test. I do have the data. I can't run the test yet because I haven't put the data in. So let's go back to stat, edit. Again, I want to clear list 1, so I'll go up there, hit clear. Oops, I almost hit delete again. That would be bad. All right, list 1, I have list 1. So let's go, we'll put our data in there. So it was 180. Hopefully these are the same numbers that I told you. 187, 181, 182, 185, and 181. All right, that's our data. We only had 6 data points, so obviously not a bunch of data, but now I can run the test again. Stat, tests, t-test. I just hit the number 2. It pulls up t-test rather than arrow down and then hitting select. It says, what's your null hypothesis mean? Oh, I hypothesized that it was 180 yards. That's what we're assuming to be true. My data is in list 1. Again, always leave frequency at 1. We want it to be greater than, so let's go over here to a greater than, select that. And then we just go down to calculate. We hit enter. Again, notice the T, and I'll jot that down, 2.39. And the p-value, 0.031. We'll go one more decimal, 0.0312. And I will tell you, they typically will do T and Z values to 2 decimal places because that's how they're read in the table. And they'll usually do the p-value to 4 decimal places because that is how they're read in the table as well. All right, but anyway, let's go back to our problem. Oh, here, notice real quickly. They calculated the sample and the sample standard deviation. That's what they use to calculate T. T is a formula very similar to Z. T is x bar minus mu, but instead of sigma over the square root of n, it's S over the square root of n, because I don't have sigma. So anyway, we don't have to calculate that, but if we did, we would get that T value, that 2.39 number that they gave us. Okay. So back to what we're writing out. So the T value we got was 2.39. The P value was 0.0312. And we're checking to see if that's less than or equal to my 5%, which was alpha. And in this case, it is. Again, if it helps you to change those 2 percentages, 3.12% and 5%, we see that, oh yes, it is less, so I am going to reject the null hypothesis. Remember, p-value, 3.12%. there's only a 3.12% chance that the null hypothesis is true. We had a cutoff of 5%. That's less, so we say, I don't think it's true. So step 4, we reject the null hypothesis. Notice that's why we have to state what the hypotheses are, because if you say reject null hypothesis, but you don't have a null hypothesis, nobody knows what you're talking about. So 5, we rejected it. We don't think it's equal. So we're going with the alternative that we think it's greater. And the question says, is it greater? And we say yes. It appears the average distance is greater than or exceeds, or however you want to say it, 180 yards. And again, we've come to another conclusion based on our p-value. Now, I will tell you on the computer, because a lot of people don't have technology, they can't find the p-value exactly on a t-test. You can on a z-test based on the table, but the t-table is set up a little bit differently. So on the p-value, when you do a t-test, they're going to give you an interval of numbers it's from. So they'll say, for instance, less than 0.01, so less than 1%, between 1% and 5%, between 5%, and I don't know where the equals and the not equals, obviously we can't have it on both, and 10%, or greater than 10%. And so since 3% is between 1 and 5, we would select that one. So they're going to give us a range of values. We have to pick where our value is. But usually they do it less like that. This might say, you know, less than 0.01 instead of writing it out in words. I don't know. Okay. So anyway, do bear that in mind. You'll see that as we do tests, when we do the homework, and you can ask me when we're doing the live sessions to help you interpret that if you'd like to. All right, so that's it. We will do one more of these problems. Now, just so you know, and the book says we've already met all these requirements. The requirements, let's just list these real quickly. Sometimes they call them the assumptions. The big one we have to worry about is data is normally distributed and remember, if the data itself isn't, or n has to be greater than or equal to 30. If we have a large enough sample size, then the sampling distribution is normally distributed even if the data is not. That's the big one. They may ask you some more in the homework. We'll go through those as need be. Okay, but that's the big one for both Z and T. All right, so do bear that in mind. Sometimes to see if it's normally distributed, if you have a small sample, they'll make you do a normal probability plot. They may make you do a box plot. They may have you do a histogram. So they'll ask things like that. But you'll see that as you go through the homework. All right, let's just do one more of these just to make sure we have a good feel for this. We may be running a little bit out of time. So I apologize for that if we are, but it'll give you some more examples to look at, which I don't think is a bad idea. So this is 9118, and it's on page 406 as well. It's called dirt bikes. It says dirt bikes are simpler and lighter motorcycles that are designed for off-road events. Specifications for dirt bikes can be found through Motorcycle USA on their website, www.motorcycle/usa.com. I guess it was dash. A random sample of 30 dirt bikes. Okay, so we know this. N equals 30, a random sample. Oh, that was another thing here. This has to be a random sample. I should probably list that. That's why they're telling us that. A random sample of 30 dirt bikes, notice 30, I don't have to know it's normally distributed because sample size is big enough, have a mean fuel capacity, that's X bar, because it's the mean of the sample, of 1.91 gallons. With a standard deviation, listen to this sentence, a random sample of 30 dirt bikes have a mean fuel capacity of 1.91 gallons with a standard deviation of 0.74 gallons. They said standard deviation right in the same sentence that they said a sample of 30 dirt bikes. So that standard deviation is S. It's not sigma, which is important because that means it's going to be a T test, not a Z test. So even though they gave us the standard deviation this time, they told us it was from the sample. So this is the sample standard deviation. 0.74 gallons is my standard deviation. And then the question says, at 10% significance level, do the data provide sufficient evidence to conclude that the mean fuel tank capacity of all dirt bikes is less than 2 gallons? So at 10% significance level, is there evidence that average fuel tank capacity is less than 2 gallons? All right. Now, one thing to notice, we didn't do any problems that were a not equal, but a not equal, it would say, are different from 2 gallons, or has there's been a change from 2 gallons. That would be a not equal. But in this case, my null hypothesis, we're going to assume mu is equal to 2 gallons. The question we're asking, though, the alternative is mu is less than 2 gallons. That was the question. We think that might be true because notice X bar was 1.91 gallons, which is less than 2 gallons. But again, is that enough to say that the average is less than 2 gallons, or could that just be sampling error? If it's not sampling error, it has to be due to something else. Well, the something else would be that the actual population mean is less than 2 gallons. All right, so we go there. The alpha they gave us 10%, so 0.10. We're doing a T test because we don't have sigma. We have S, the sample standard deviation. So we'll figure out what T is. We will figure out our P value. We're going to compare that to the 0.10, which is alpha, to make our conclusion. All right, so now let's flip back over and we'll get the calculator out so we can do the calculations. All right, so let me clear this. I'll clear my drawings as well. All right, so let's see. We're going to go stat, tests, t-test. This time we don't have the data. We have to go to stats. We have to input the individual calculations we have. So again, our assumed mu is 2 gallons. That's what we're assuming to be true. Our X bar, they told us, was 1.91 gallons. The standard deviation was 0.74. You can put the 0 in front of that if you want to, but you don't have to. And our N was 30. We wanted to see if it was less than, so we have to choose the less than, and that's it. And we're going to let the calculator calculate all these things for us. All right, so let's see. I have a T of negative 0.666 and a P value of 0.2553. All right, so let's go back to finish our write-up. All right, so here we are. We got a T value of negative 0.666. Oh, we only wanted to go to 2 decimal places there. Negative 0.67. The p-value was 0.2553. 0.2553. Again, this is 25.53%. So there's a 25.33% chance that mu really does equal to percent. That's not small enough, so we can't throw that out even though our sample mean was less than 2 gallons. So notice this is less than or equal to 10%, and we say, oh, no, it's not. So we'll cross that out. So we say, oh, since it's not less, I do not reject the null. And so our conclusion is no. And a lot of times they'll state the percentage. Oops, I moved over a little further than I wanted to. No. At the 10% significance level, I usually don't because I'm too lazy. The data is not sufficient to show the average, oops, I should probably clean that up, huh? The average tank size is less than 2 gallons. All right, let me point something out. Again, notice our X bar was 1.91 gallons. It was definitely less than 2 gallons, but that was just the sample mean, not the population mean. We're trying to predict the population mean. And so we're trying to decide, hey, is that far enough away? Well, clearly it's not, because that would happen 25.53% of the time that we'd be that far away or further from 2 gallons if the average of the population actually was 2 gallons. Now, another thing that I want to point out is the way we worded the solution. We say, no, the data is not sufficient to show the average is less than 2 gallons. The conclusion's always in terms of the alternative hypothesis. Notice what I didn't say was, no, the data suggests mu is equal to 2 gallons. How in the world can we get an X bar of 1.91 gallons and that proves the population mean is 2 gallons? You cannot prove the population mean is equal to anything unless you have all the population data. So do not word your conclusion as, oh yeah, it looks like the average is 2 gallons. No, we got 1.91 gallons. It's just not far enough below 2 gallons to say that we think the population mean is actually below 2 gallons. So do be careful about that. All right. That is all I wanted to show you. We did a lot of examples. One good thing, in my view, you may not agree with, but usually in class, I don't have time to do 4 examples. I was glad I was able to today. Hopefully the lecture is not terribly long, and hopefully you can get through it, but you have a few days to get through it. So we'll discuss this in class. I'll answer questions on this on Thursday. And again, if you have any questions on the homework, we can look at those as well. All right, well, that's it for today. Hopefully that makes sense to you. Do practice this, and I think you'll find that you are going to get the hang of it. The more you do, the better it'll be. And just so you know, hypothesis testing is vitally important. It's what we do for the rest of the semester. So you won't just see it on this exam, you'll see it on the 3rd exam and on the 4th exam and on the 5th exam. So do get a hold of this, and I think you can do this. So just keep working hard and you can do this.